So by combining these two layers, people call it and name it as a double layer. And also, besides of this such kind of an ionic structure, also all the other parts should be filled with some kind of dissolvent molecules like water. And these waters are usually polar, which means having a lot of the strong molecular dipole. So they can have some kind of a unique structure by solvating the ions or by aligning their dipoles upon a given electric field. So all these things are determining the complicated EDA structure. And on top of here, electron transfer coming from the metal electrode to the chemical species in the electrolyte, actually that determines the called electrochemical reaction. So many people think that the electrochemical property should have an intimate relationship with the EDA structure. But unfortunately, nobody knows what it is exactly until now, and it has been regarded as some kind of the long-standing challenge in the field of this electrochemistry. So there are many reasons why it's really difficult to understand it, and mostly because we cannot really see it because it's in the buried actually space. And also from the modeling kind of point of view, it has kind of the complexity, which will be actually illustrated from now on. So this kind of electric double layer should be formed at the interface between the metal electrode, solid, and electrolyte, which is usually the liquid. So solid theoretically is defined as a kind of the long-range ordered atoms, and actually they make some kind of the unique electronic structure like a band structure. And also, if we want to simulate electrode, we need to know the way to put some extra electrons in or take some electrons out, which means we need some kind of the explicit treatment on these electrons, which means we need a quantum mechanical treatment for there, like the density functional theory. For the electrolyte, which is liquid, should be very dynamic, and they are characterized by the mid to short range orderness. This means a certain dynamic simulation is really required to fully understand the liquid structures. Particularly for the EDL relaxation time is known to be occurs like order of nanoseconds. So this means that at least we need some kind of the nanometer scales and nanosecond scale of the simulation is needed for here, which cannot be achieved through the ab initio MD type of the simulation. So I would say that classical molecular dynamics will be the only possible way to have a proper understanding of this liquid structure of the EDL. So this is, in short, is a heterogeneous system because it's an interface and it has the intrinsic heterogeneity, so which makes the modeling of this system be very difficult. So actually, to tackle such kind of a problem, our group has been working on some kind of the method development and actually applied it to understand the EDA structures. So from now on, please let me briefly actually explain the theoretical setup for our simulations. So as I explained, I think that the most natural choice of the simulation method will be the electrode should be treated in a quantum mechanical levels like the density functional theory, and the liquid should be treated with a classical MD. So naturally, the QMMM type of the Hamiltonian will be the one choice to describe such kind of the interface. One thing that I have to note here is that when we talk about the QMMM type of the technique or the ab initio MD, that the QM part Hamiltonian is from the dynamic point of view, that should be the classical, actually the dynamics, classical Hamiltonian under the quantum mechanical potential energy surface using the Born-Oppenheimer approximation. And in such kind of the QMMM type of the theory, always the most headache part will be the interface Hamiltonian. But here, if we neglect any kind of the strong chemical interaction between the liquid and for that one, where the electrostatic interaction and the van der Waals interactions are modeled using the pairwise potentials. Of course, if we arrive at such kind of the mixed Hamiltonian, if you obtain the classical equation of motion, and if you solve it, numerically solve it on a discretized time grid, that is the conventional QMMM. But still the main problem is if we want to do such kind of the conventional QMMM, all the computational cost is limited by ab initio part of your QM regime. And also in this case, it's an electrode, metals having lots of atoms and also lots of electrons. So the total time scale can be hugely actually limited by the ab initio dynamics of your QM part. So we cannot use that one. So instead of doing that one, what we thought is that we view the kind of these dynamics, classical dynamics, as the kind of the chain of states, likely what the potential mean force people are doing. And we think that our system, characterized by their classical positions and momentums, And kind of the electron densities can be thought as they are fluctuating as a function of time, and they are changing from one state to the other. And doing that one, we can integrate out the all degree of freedom for the liquid part by considering that as a kind of the best-like quantity. Then we can define the Helmholtz-Freenet functional, which depends on the electron density of your QM subsystem and structure. Then from there, we can formally write down the way a variation theory that can minimize your Helmholtz-Freenet function upon the electron density changes. And also we can optimize their positions, nuclei positions. So which can be achieved by simply adding the mean potential coming from mean electrostatic potential coming from your liquid dynamics. So this is the mean field coupling of the QM and MM rhythms, which is usually in the field called as a mean field QM MM technique. And the way to implement it is that we can iterate the static density function optimization, not dynamics. And also we can do a separate classical MDs, but under using this the static DFT optimizations, electrostatic potentials, and the van der Waals potentials as a fixed potential. Then we can sample the mean potential there, and we can bring it back to the static DFT optimization. So we can iterate these two consecutive DFT optimization and simple classical MDs until we obtain a self-constant solution. So particularly, we named our methods as density functional theory in classical explicit solvers. And I would not say that we are the kind of the first group who developed such kind of an idea. So similar or quite same ideas have been proposed by the previous groups, and so which are listed here. And we have been actually coded this method in our computer code, and we have been developed required potential for the last couple of years. So let me briefly, because it's more method kind of the symposium, so let me briefly summarize the key features of our DFTCS. The first thing will be the cost effectiveness. So by neglecting the ab initio MD part, we think that that's going to be reasonable, particularly for the solid liquid type of the system, where the solid would show more just vibration, more the phonon dynamics only. And also the entire computational cost consists of usually the several DFT calculations, just conventional optimization, and several MD simulations. So assuming that each of these require around an hour, that's gonna be on order of a day job. Also, we are using the technical using the grid-based coupling, which includes the FFT-based boson solver. So it actually naturally includes the long-range electrostatics. Also, it has the well compatibility with the plane wave DFT, also which is good for modeling the solid system. Also, we are relying on to the well-optimized liquid force field. I would say that usually, in principle, the ab initio MD will be the good choice. But in most cases, because of the choice of the exchange correlate potentials, van der Waals corrections, and some other the basis levels, we often see that the ab initio MD, firstly describe the liquid structure. So I would say that further, if we use the well-optimized force field, then at least the errors can be trackable and can be curable. The only headache part will be the interface part, where we think that the electrostatics, by using the grid-based coupling, is more or less seamlessly treated. That's going to be fine. But the more complicated part will be the interface of van der Waals instructions. So using a kind of, throughout the previous studies, we showed that we developed a way to systematically develop the required van der Waals potentials parameters based on the first principle calculations. So which can be claimed as the first principles-based multiscale approaches. And we found that by throughout such kind of things, we can accurately predict the interfacial tensions and resulting the contact angle values, which are comparable with the experimental data. So that's gonna be the overall outline of our method and how we treat the solid liquid interfacial system. And to understand the electric double layer, also we need to think about then what should be compared with the results coming from our computer box. So we looked back to the kind of previous history of the electric double layer in the theory development, and we found that the EDL capacitance shows a kind of the two peculiar peak behaviors, which is called as a Coleman shape behavior, when they measure it using the very clean single crystalline electrode with the also very clean, dilute millimolar level of the concentration of the electrolyte. And people really try to understand what's the reason for these two peaks. First, like the Helmholtz kind of conceptualize the capacitor kind of things with the two-plate capacitance, which should show no change of your capacitance upon their potential changes, which is apparently different from this one. And also by solving the famous Poisson-Boltzmann equation, and GUI-Chapman model has been developed, which can capture the deep behavior here. But the problem is that once you charge your electrode into the positive side or negative side, it goes to the infinity, which is catastrophic behavior. So to kind of appease such kind of the problem, people added like more ad hoc type of the treatment to the theory, which is called as a Stone model, and this gives you some kind of the upper bound for the capacitance. So, but still, I would say that this is a two-peak behavior, but this cannot be called as a two-peak behavior rather than one deep behavior, which is way from, qualitatively way different from what it is. And I would claim that the reason why is because the Poisson-Boltzmann theory, which is a kind of the dilute concentration limiting theory. The problem is although your bulk concentration is low enough, but once you start to charge your electrode, that's gonna draw the ions nearby. So the local ion concentration cannot be low anymore. So that brings a kind of the significant problems, particularly when we charge your electrode into the positive or the negative sides with a certain amount. But at least what we learned from this kind of the historical development is that the EDL capacitance is a kind of the right quantity to be compared with the simulations. And we aim to reproduce the common-shaped behavior from our simulation. One remaining kind of the hurdle that we had was how we can define our electrochemical potentials from our solid liquid interfacial simulation. But what we found is that because we treat our metal electrodes in a quantum mechanical level, we exactly know where our Fermi level with respect to the vacuum level. And according to the Trossard's definition of the absolute electrode potential, your Fermi level location with respect to the vacuum is defined as the absolute electrode potential. And by shifting it by the 4.4 volt, we can convert it into the potential versus well-known standard hydrogen electrode values. So we can do it more the straightforward manner. And by combining this definition with our DFDCA simulation, we were now able to do simulation for the electric double layer. So the system we chose is the single one on a single crystal, which is already known that I think I'm stuck.
It's okay. Take your time.
혹시 들리시나요? 괜찮나요?
Yeah. Yes.
Yeah, sorry. So I think if there was some kind of buffering, so maybe it seems to be okay. I'd better turn off my video for better bet.
Take your time. It's okay.
Yeah. Let me move on. So we have the silver on a single crystalline. We chose the dilute sodium fluoride system, which is known to have the very doesn't have a strong chemical interaction between this region. And we also use the dilute limit electrolyte, which means that only either sodium or fluoride ions are included in our system to compensate the extra charge stored in your electrode. Because we do the all atomic simulation and we treat the electrons explicitly, we know where the accumulated electrons are and what the orientations are, and we have the all atomic resolution data. Also, what it got is that we can change the excess charge density, which is stored in the interface by changing the extra number of electrons in your quantum mechanics region and extra number of ions in your MD simulation. We can control the surface charge density, which is shown as the sigma value here. And by using the definition that I showed you in the previous slide, we can measure where your potential is. And from the separate simulations, we can collect all these red dots, which is interpolated using the black line, as you can see here. Usually, actually, in our simulation, we control the sigma surface charge density and we measure the potential. But in reality, in the experiment, they control the potential and measure the charge density. So it's better to flip the X and Y axes. And actually, then the slope defines your differential capacitance. But interesting thing that we found is that there is some kind of negative slope region. So we'd like to understand what it is, if it is kind of an artifact or has some kind of the meaning there. The final understanding about the peculiar behavior can be obtained from from the macroscopic thermodynamic argument. So we can write down the total Helmholtz free energy for the interface, where including the electronic work, which is ED sigma, usually called as a QV. This is the the potential, this is the charge density. This means that for the constant volume temperature cases, we can calculate the electronic work in this manner. And also the problem is that we do the simulation from the thermodynamic point of view, do the simulation of the constant sigma ensemble, while experiment measure the constant potential ensemble. So what this means is that on the E potential charge plane, once you have some kind of the third order polynomial type of the behavior, if you integrate out your free energy, Helmholtz free energy should show some kind of the first order double wide type of the behavior. And this means that there can be a kind of the phase separation in this region, and we can construct the coexistence line using famous Maxwell tile construction, just a kind of the undergraduate physical chemistry kind of a thing. So this is the simple linear line. So if you go back to here, it was the integration, so that the other direction will give you the differentiation, will give you one horizon line. And once you flip your x and y axis, then you will have one vertical line. Then by including some kind of the Maxwell tile reconstruction, we can do the derivative of this curve. This gives you the differential capacitance. So the black line is the one that we obtained from there, and these are compared with experimental data. So I would say that we are kind of the first group who succeeded to reproduce the two peak behaviors, all from the bottom-up type of approaches from the all atomic type of the simulations. And also we found that the peak positions in the relatively right positions and the capacitance values are quite comparable. So this means that we are kind of quite ready to understand what's the molecular origin of these two peaks. Toward that one, we introduced the two analogical physical variables. One is the distance, charge separation distances, and the other one is the effective dielectric constancy. So I would say that we don't control this one. This is for analysis by mapping our situation with the more simple two-plate capacitances. So here's what's going on. So for the anodic comp, we found that inverse D, which is shown as a red curve here, dramatically increases, which means the distance decreases. This is because of the phenomena called as electroabsorption. Once we charge your electrode with a positive charge, the fluoride anions start to be accumulated with preserving the hydration share. But after a certain moment, actually, it starts to lose its hydration share and it starts to stuck onto the surface, which is called as the electroabsorption behavior. And this decreases the charge separation distance pretty dramatically. This increases the inverse D so that it increases the capacitance. We also found that the dielectric constant decreases very rapidly. This is ascribed to this ion water interactions, which is quite strong. So the stuck ion starts to flip the direction of the water dipole. So it cannot screen the electric field coming from the electrode anymore. So the effective dielectric constant decreases so that the capacitance decreases again. More funny thing happens for the cathodic hump behavior, the other directions. We found that the inverse D doesn't change much, which is also because the cations, alkali metal cations, are relatively hard, so that it keeps its hydration share in a more intact manner. So it does not want to lose its hydration share. So inverse D stays more or less there. But we found that the dielectric constants increase then decreases. Funny behavior. And the reason why is because at the lowly charge, when your surface charge density is low enough, mostly the interfaces consist of the waters with few number of ions. And what happens here is that once you charge your electrode, this first layer of the water starts to stand up. It offers oxygen to the second layer. The second layer of water also starts to stand up, and third layer again. So it shows a collective standing up behavior, which dramatically screens your electric field coming from your electrode, so that effective dielectric constant increases. But also simultaneously, this brings your ions nearby into the so-called outer Helmholtz plane layer. So it flips back those water molecules direction. So it cannot screen your electric field anymore. So by competing these two factors, it shows up and down type of the behavior on your effective dielectric constant. So finally, I'd like to just explain then how this kind of the funky behavior of your effective dielectric constant can bring you a peak behavior of the capacitance. So for the interfacial potential drop, electrochemical potential can be simply understood as the kind of the proportional to the ratio of your surface charge density divided by the dielectric constant, if you think about the two-plate capacitance curve of the motor. So near a certain kind of the sigma, what you can see here is that there is a kind of the sigma is high, but also your dielectric constant is high. And this point will be the sigma is low, then also your dielectric constant is low, so that these two kind of situations can have accidentally have the same potential drop. In other words, this means is that in the experimental situation, when you control your potential, then at a certain potential, at the same potential, these two states can be bistable, so that using the sigma as a kind of the variable, we can write down the Landau type of the free energy density using the first order polynomial, also where the field interaction term, all the cubic electron work terms are also included here. And using the Landau-Collatine curve theory, we can write down the kind of the time-dependent change of your surface charge density. And at an equilibrium where your sigma doesn't change upon the time changes, you can finally arrive at your equilibrium potential should show some kind of the third order polynomial type of the behavior, which brings you the two-phase coexistence and phase separation behavior. And because of the phase coexistence behavior at this region, we can argue that there is some kind of the first order type of the phase transition, which brings you a very sharp peak of your capacitance behavior. So here's the summary slide. So we were try to understand we really try to reproduce the kind of the two peak behavior, common shift behavior, which is experimentally shown, but have not been fully explained for the last 100 years. And by developing our new method, finally we arrived at our own answer, which is that the one peak is because of the electroabsorption behavior, and the cathodic peak comes from bistable phases, and their kind of the phase transition behavior actually manages to make such kind of the peak behavior there. And also we are kind of extending our simulations to include some kind of for the more finite ion cases by developing so-called kind of the ion bath kind of situations. The reason is because also it is known that your capacitance behavior can be dramatically changes if you change your bulk concentrations. So we'd like to get some understanding what kind of situations are happening there. And throughout such kind of an effort, what you are aiming for is that it's a kind of the big picture direction. What you want to do is that. So here are some kind of the entities that is characterizing your EDA structure. So if we know some kind of the way to perturb your EDA structure, and experimentally, people can measure the EDA capacitance changes. Also, people can measure the electrochemical property changes from experiments. And by doing our DFTCS simulation, we can map and assign why such kind of the capacitance change happens in the EDA with respect to the structural changes, so that we hope to establish some kind of the EDA structure and activity kind of the relationships eventually. So here's my acknowledgement slide. So our group members, and I would just like to particular thanks to the Dr. Seung-jae Shin, who walked on to all the stuff that I talked today, and who left our group and now doing the postdoc in our own work group, and also Professor Hyung-joo Kim, who is also our previous group member, who contributed a lot into our initial development stage of the density functional theory, classical experience servant, and also